Hey, it's you again. You're here for another lesson of physics. And today we're going to talk about capacitors, section 19b. I think you're ready. Alright, let's go ahead and talk about capacitors and the need for capacitors. Alright, so one hindrance to early investigators of electricity was that they could not store a charge. They might get a charge, but they had nowhere to store it. They could accumulate charges by using friction, but these charges were soon leaked away. And the investigators did discover that it is easier to store charge using two conductors separated by an insulator, a positive charge on one and a negative charge on the other. And then that was easier than just having a conductor by itself. So if you had two conductors separated by an insulator, they figured out that they can store a charge. All right. In the mid-18th century, two men, a Prussian cleric and a Dutch physicist, independently developed an efficient charge storage device, and this was called a Leyden jar. So here I have a picture of a Leyden jar that I pulled from the internet, and it kind of shows how a Leyden jar works. Okay. A Leyden jar is a glass jar with a lead coating on both the inside and the outside. There's lead. In this case, they have metal foil on the inside and outside, and then there's a glass jar. A conducting rod is inserted through an insulated stopper. Right, so this is an insulated stopper where you can use rubber. In this case, on this one, they're using dry wood. And it is connected to the inner metal surface by a metal chain. So we have a metal rod inserted through a rubber stopper or an insulated stopper. In this case, they use wood, and a metal chain that makes contact with the coating on the inside. If this is positively charged, then these guys are positively charged as well. On the outside, it's negatively charged. Now this acts just like the original storage charge device, because it has a positively charged and negatively charged metal or conductor separated by glass, which is an insulator. And this would use just to hold a charge. And the Leyden jar would stay charged for a reasonable amount of time, so it became a very popular way to store charges. Now, nowadays, we use something different. We use things called capacitors. A capacitor are two conductors separated by a material called a dielectric. Now, possible materials for dielectric include air, glass, water, or sometimes they're even vacuum sealed. So the modern descendants of the Leyden jar are things that are called capacitors, and this is very common in electronics today. So often capacitors are constructed as parallel plates with a dielectric between them. Each metal plate contains a charge opposite of the other. So if there's two plates, one is positively charged and the other is negatively charged. And these capacitors have the ability to be discharged. Alright, so what we're going to do right now is we're going to go ahead and look at a diagram of a capacitor. Right here I have a positively charged side and a negatively charged side, and in between them is a dielectric. Now remember, the dielectrics can be air, glass, water, vacuum sealed, and these are just common dielectric materials, and they have the ability to be discharged. All right, this is a symbol for one of the symbols for a capacitor. Alright, so cool there. And all it is really just two charged plates with a dielectric in between it. Now, the dielectric constant is the ratio of a given electric field strength in a vacuum to the same field passing through a particular material. Now, all of this is cool to know, I guess, but the important things are, one, we use the letter kappa in order to, it looks kind of like this, in order to signify a dielectric constant. The kappa is greater or equal to 1, and here are the common kappa values, the dielectric constants for common materials. If I decided to use air as a dielectric, the kappa value would be 1.0005. If I use paper, 3.7 or about 4. Right? If I use porcelain, 6.5, and water as a dielectric, constant would be 80. Now, why is this so important? Because one possible problem that you could have either on the homework or maybe on the test is I might not give you the kappa value. You might have to look up these dielectric constants. This is table 19-1, found on page 437 in your book. So you might want to have access to this when doing your homework. More than likely, I would give you the dielectric constant, but I don't have to. So make sure that you guys are referring to this table. Now, E sub 0 is represented as the reduction in the vacuum field strength. And if I ever wanted to find the electric field strength in a dielectric, I would take the E sub 0 and divide it by kappa. So this is one possible equation that you could use. And just giving you guys a heads up that this lesson is going to have a lot of slides for you to copy down with a few different formulas, just like this next one. Now the potential difference is reduced compared to a vacuum capacitor. So in this case, the potential difference of the dielectric is equal to the vacuum potential difference divided by the dielectric. Probably not going to use this equation that much, but something for you guys to have in your notes. All right, just notice it would vary depending on the kappa value, and the kappa value depends on the material you use as a dielectric. Capacitance has been found to be a ratio of the entire charge on a conductor and well, we're going to go ahead and say voltage. Now, capacitance is a really important thing for us to find. So this is very likely a formula that you guys will have to use, right? But if given kappa values and a few other different values, we can go ahead and find the capacitance using this other formula, where kappa times the permittivity of free space, we'll talk about that, times the area of each plate divided by the distance will give you the capacitance. So this is a very important equation for you guys to use and to have written down. All right, this is something that you guys are very likely going to use. All right, so A is equal to the area on each plate, and we're going to use the units meter squared. D is the distance between the two plates, because remember we have two plates separated by a dielectric. Right? And then we would have a positive charge on one side and a negative charge on the other. And the distance between them would be represented in this equation. Epsilon sub 0, so this letter is Greek letter epsilon, sub 0 represents the permittivity of free space. And then just so you guys know, it's going to be this number. Now, we're going to use 8.854 times 10 to the negative 12 when we're talking about coulombs. All right, so this is just kind of a number that we're going to have to use. All right, so notice that this is the letter K. It's not kappa, so it's not going to change based on the dielectric. It's just going to be this number. Cool? Cool. Moving on. Now, the farad is the SI unit of capacitance. The farad is named after, you guessed it, Michael Faraday, and is defined as 1 coulomb per volt. So, if I have 1 farad, it's 1 coulomb per volt, and this is the official SI unit of capacitance. Now, in electrical components, it is more common to use microfarads or nanofarads or picofarads because of the size of 1 farad. 1 farad is 1 coulomb per volt. So we're more than likely going to use these ones. Now, if you ever do see the term micro, nano, or pico, we want to go ahead and associate them with these, with these exponents. All right, so let's go ahead and look at this example. Or just kind of real quick, if I had 3 microfarads, that's the same thing as 3 times 10 to the negative 6th farads. Right? So we want to be able to use these conversions if given. All right, now, the last 2 things we need to talk about are connected capacitors, because oftentimes with electronics they connect them and we have to be able to figure out the total capacitance. And there's 2 different types of ways that we will connect capacitors. The first way is when we connect them in parallel. And here's a diagram that's showing 2 capacitors connected in parallel. Now notice they are side by side, and the way that I kind of remember these guys right here is it looks a little bit like we have these guys side by side, and then this side is running parallel with the other one. All right. So this is an example of what it looks like in parallel. And this is the best case scenario, because if I ever ask you to find the capacitance of 2 capacitors connected in parallel, you are simply just going to add them together. All right. Sound fun? Like if I said that this has a capacitance of, we'll just say 3 microfarads, and this has a capacitance of 5 microfarads, then we can say 3 microfarads plus 5 microfarads is 8 microfarads. Okay, so that was cool. This is always what I'm going to call the best case scenario. All right, because it's really easy to add them together. All right, so this is what they look like when they are parallel, so they're when they're right next to each other. If they are stacked on top of each other, or we call them they are in series, we can use these two equations. All right, so 1 over the total capacitance is equal to 1 over the first capacitance plus 1 over the second capacitance. We turn them basically into fractions, and we can add them together this way, or we can use this equation. It might seem a little bit more simplified. Now remember, we can connect them like this in series, and if they are in series, we don't always just have to have 2. You can have 3 or 4. So if I had like 3 capacitors, right, I can say 1 over the total capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. We can kind of expand it if we needed to, if we have to add more than 2 capacitors together, if they are in series. All right, that means that this can be the same thing. This can be C1, C2, C3 over C1 plus C2 plus C3. We can just expand them. All right, so you can use either equation if we had to. All right, so like let's say capacitor 1 has a capacitance of, let's say, 5 microfarads, and this has a capacitance of 5 microfarads, then the total capacitance, all right, would equal to 5 times 5 over 5 plus 5 microfarads. So I get 25 over 10 microfarads, which is going to equal to 2.5 microfarads. All right, so we can use this equation to kind of find the total capacitance. That is it. That's all we have to talk about in this lesson. Enjoy the homework. Peace.